Okay, so here's a graphical representation of a Riemann sum. This is a website called Intmath. So you can basically choose some function here and look into their integrals. So I wanted to show you what the graph looks like. So for example, if I have left sum, as you can see, these rectangles, top left corner touches the graph, right? And the actual value of this is, let's see, 18. So the area under the graph, if you actually knew how to calculate it, it's actually 18. Okay. And if you just use maybe 5 or 6 rectangles, you get a big error. It's like the error is off by 1. Right? Here it says the exact integral is calculated like this. We're going to talk about this definite integral later, but the exact value of the area under the graph is 18, whereas our Riemann sum is 19. And as you increase the number of rectangles, you see that it's getting closer and closer, and eventually it becomes like what, close within 0.1, right? So the error is less than 0.1. Let's try another example. By the way, we actually did this calculation last time. We tried to approximate 0 to 1, right? And I explained that the actual value is 0.333, and in that we tried we actually tried 10, right? So with 10, if you use left endpoints, it's 0.285. If I use the right endpoint, it's 0.385. You recognize this number, I had that last time. And if you use other ones like middle, becomes better, and trapezoidal is better, and if you use Simpson's, it's even closer. Okay? So I'm going to explain what these other methods are. So let me try to use another one, e to the x. Let's try to integrate e to the x from 0 to 3. And if I use, let me just use just six rectangles. Okay. So first, what's the lower? So lower Riemann sum means you always underestimate. In this case, it's same as the what do you call it? The left sum, right? But if you used this one, as you can see, the left side for y equal to x squared, the left side is a right sum, whereas the right side is a left sum when you do the lower one. If you use the upper one, it's going to always overestimate. That's what an upper Riemann sum is. Explain what left is. Right means that the right top corner touches the graph. That's what right sum is. Middle. What does middle sum mean? The midpoint of the top is on the graph. That's what it means. That's the middle point. And because this is, so in one chosen rectangle, you can see that part of it is an underestimate and part of it is an overestimate. You can kind of see that these two will kind of cancel, and you're going to get a better approximation than just having a left sum or right sum. So compare this. This middle sum was only about 0.4 wrong, it was off by 0.4. If you use something like left sum, it's going to be off by 0.7. So definitely middle sum is better. What's a trapezoidal sum? Trapezoidal is when you use these trapezoids. If I decrease the number, it might be more apparent. See, this one thing is what we call a trapezoid because these two sides are parallel. Right? This side and that side are parallel. So this is a trapezoid, and you're using trapezoids to approximate the area. And again, you see that trapezoids have, it's especially closer to the graph if the graph is closer to a straight line. So if it's more bent, places like this, it will have more error, but over here, it will have less error. Yeah. So trapezoids are a little better than the left sum or right sum, but unfortunately, it won't be as good as the midpoint ones. There's a mathematical theorem which shows that trapezoids have like twice the error of midpoints, usually, for functions that are twice differentiable. All right, now you have the Simpson's rule. Okay, Simpson's rule is really hard to say. What it is really, it's trying to use these shapes. So this is one shape where the top part is a parabola. Okay, so it uses parabola to approximate graphs. Okay, so let me show you something that's not. Maybe I should increase this. Okay, so here I have 1 and 2 shapes. This is 1 and 2. The second one is using a parabola to mimic the graph of 2 plus sine x. And because parabolas are allowed to bend, you can see that it's very close to the actual thing. And that's why Simpson's rule is such a good way to approximate things. Now it turns out that you could do this with like something like a rectangle, but the top shape being a cubic, for example. Or you could make a quartic polynomial. You can make even more complicated things, but then it becomes too complicated to be useful. And in some cases where the function is not that much differentiable, it actually leads to bad results. So usually when you have a function which is smoothly varying, then Simpson's rule it's the most effective way of approximating an integral. All right. Okay, so let me show you a few other ones. So for e to the x, I just wanted to show you that in all of these, when you take Simpson's, for example, it's a very good way to approximate the actual integral. See, already at 14 intervals, it's correct until what? The 3 digits, right? If you increase to 20, it's very close. So Simpson's rule is pretty cool. I guess that's one of the things that you get out of this. So the reason I'm showing you this graph is I just wanted to show you there are various ways to use rectangles and maybe possibly other kind of shapes to approximate the area under the curve. And of course, if you increase the number of subintervals, then you get better and better approximations. But also, there's this nice method called Simpson's, which is the most effective way to approximate if you have a graph.